3 times more stored energy than the world's biggest international fusion project. 1.5 times the size. Built entirely with domestic materials, with 0 foreign components inside it. And it just passed every single test. This week, Chinese engineers finished building the largest superconducting magnet ever constructed for a fusion reactor. A machine designed to contain plasma hotter than the core of the sun itself, floating in mid-air, touching nothing. This isn't a concept video. This isn't a rendering. This is a 582-ton piece of working hardware that just passed every acceptance test thrown at it. And it might be the single biggest step humanity has taken toward unlimited clean energy in years. Stick with me, because by the end of this video you're going to understand exactly what this machine does, why containing something hotter than the sun is one of the hardest engineering problems on Earth, and why China's own timeline now puts working fusion electricity only 4 years away. If you've never seen how close we actually are to solving the energy problem for good, hit subscribe now, because this story moves fast from here. Here's the headline version. China's Institute of Plasma Physics, under the Chinese Academy of Sciences, has completed and successfully tested the largest superconducting fusion magnet ever built. A D-shaped toroidal field magnet measuring 21 meters long, 12 meters wide, and weighing 582 tons. For comparison, that's roughly the weight of 2 fully loaded Boeing 747s, shaped into a precision component that has to function at temperatures colder than deep space on the outside, while helping contain plasma hotter than the surface of the sun on the inside. This magnet stores 3 times the energy of the equivalent magnets being built for ITER, the International Thermonuclear Experimental Reactor in France, currently the largest fusion collaboration on the planet, involving dozens of countries. China's version is 1.3 times larger by volume, and according to state researchers, it was built using entirely domestic materials and manufacturing, with no reliance on foreign suppliers for the critical components. 6 years of engineering work went into it. 47 patents came out of it. And it just passed every performance and acceptance test it was put through. To understand why engineers around the world are genuinely amazed by this, you need to understand exactly what fusion energy is actually trying to do, because it might be the single most difficult engineering challenge humanity has ever attempted. Fusion works by fusing light atomic nuclei, typically forms of hydrogen, releasing enormous amounts of energy in the process. It's literally the same reaction that powers every star in the universe, including our own sun. The appeal is almost unbelievable if you just look at the numbers. The fuel is abundant, cheap, and available almost everywhere on Earth, and unlike burning fossil fuels or splitting atoms in a conventional nuclear reactor, fusion produces no carbon emissions and no long-lived radioactive waste during operation. If you could reliably harness it, you'd have access to something close to unlimited, clean, safe power forever. Here's the problem that's kept fusion just barely out of reach for over 70 years of serious research. To actually force hydrogen atoms to fuse the way they do inside stars, you need to heat plasma to temperatures above 180 million degrees Fahrenheit, hotter than the core of the sun itself, which only reaches around 27 million degrees. No material on Earth can physically touch something that hot and survive, not even for a fraction of a second. So instead of touching it, you have to trap it. You have to suspend superheated plasma in midair, contained entirely by invisible magnetic fields so powerful and so precisely shaped that the plasma never once brushes against the walls of the reactor. If it does, even briefly, the reaction collapses instantly and the wall gets damaged. That's exactly what this magnet is built to do. Picture the actual engineering problem. You need a magnetic field strong enough and stable enough to hold something hotter than a star, perfectly shaped in a massive ring, running continuously without a single flaw. And the magnet generating that field has to be built from superconducting materials, meaning it has to operate at temperatures near absolute zero, literally colder than deep space, while sitting just meters away from plasma at 180 million degrees. You are engineering the coldest and hottest things humans can create, running side by side, separated by nothing but magnetic force and a few meters of vacuum. China's team also successfully tested a second critical component alongside this magnet, a high-temperature superconducting central solenoid coil, often compared to a spark plug in a car engine, because its job is to help ignite and sustain the plasma reaction once it's running. Passing acceptance tests on both of these components in the same announcement is exactly why fusion engineers around the world are calling this a genuine milestone, not just another incremental research update. But here's the question serious scientists are asking that most headlines about this are skipping right past. Does building the world's biggest magnet actually mean China is close to producing real electricity from fusion? Or is there a much bigger, much harder gap between this milestone and an actual power plant? Let's be precise about exactly what this milestone proved and what it didn't, because getting this wrong in either direction misses the real story. What genuinely happened? China built and successfully tested the single largest fusion magnet ever constructed, entirely with domestic technology, and it passed every performance test thrown at it. That's real, verified, and represents years of accumulated engineering work across a program that's produced 47 patents and dozens of technical standards along the way. What didn't happen? This test did not involve producing any electricity. It confirmed the successful development of reactor-scale components, the magnet and the central solenoid, not a working, self-sustaining fusion reaction generating usable power. And it's worth being upfront about something else, too. Independent Western verification of China's specific test results isn't currently available, since this was announced and confirmed by Chinese state researchers rather than an outside international body. That doesn't mean the claims are false. China's broader fusion program is well documented and internationally recognized. But it does mean the specific performance numbers haven't yet been independently confirmed the way, say, ITER's published results typically are. There's also a much bigger scientific hurdle that no magnet, however impressive, solves by itself. For fusion to become a genuinely usable source of electricity, a reactor has to consistently produce more energy than it consumes to run, what scientists call net energy gain, and it has to do that safely, reliably, and economically over long, continuous periods of operation, not just in brief experimental bursts. That remains one of the hardest unsolved problems in the entire field, and scientists working on China's program have been explicit that this milestone, however impressive, doesn't solve it on its own. So, here's the honest scoreboard. China now has, by measurable specifications, the largest fusion magnet on Earth, built domestically, tested successfully. What it doesn't have yet is a working power plant, or even a demonstrated net energy gain from a reactor using this exact hardware. This is a critical piece of the puzzle completed at record scale, not the finish line. But here's why fusion scientists worldwide and increasingly investors and energy policymakers are still watching this incredibly closely. Because completing the hardest component first is usually the difference between a country that's serious about a technology and one that's just talking about it. Because this magnet isn't a standalone science experiment sitting in isolation. It's one piece of a much bigger machine China has already publicly committed to finishing. And the deadline attached to that machine might surprise you. Here's the layer most coverage of this story is glossing over. This magnet isn't just an isolated engineering flex sitting in a lab for its own sake. It's a specifically designed component for China's burning plasma experimental superconducting tokamak. a next-generation fusion reactor China has publicly committed to completing by 2027. That's not a vague, decades-away aspiration. That's a specific machine with a specific target date. And this magnet is a required piece of building it. And China hasn't stopped at just one machine. The country has laid out a three-stage roadmap toward commercial fusion. Complete this experimental reactor by 2027. Target China's first fusion-based electricity generation around 2030. And eventually build a larger demonstration power station called the China Fusion Engineering Demonstration Reactor, intended to be among the first fusion power stations on Earth actually capable of feeding electricity into a real grid. If that 2030 target for first fusion-based electricity holds, even in an early limited form, it would represent one of the fastest publicly stated timelines toward practical fusion power that any nation on Earth has committed to. Zoom out even further, and there's a broader context that makes this milestone land even harder. This didn't happen in isolation from the rest of China's energy strategy. In the same week this magnet completed testing, separate reporting confirmed that coal has fallen below 50% of China's total power generation for the first time, a milestone officials specifically described as a breakthrough in the country's broader green energy transition, driven by the rapid expansion of solar, wind, and other non-fossil sources. China is simultaneously scaling up renewable energy today while placing a serious, well-funded, multi-decade bet on fusion as the technology that could eventually make energy scarcity a non-issue entirely. Whoever solves commercial fusion first doesn't just win a scientific prize. They fundamentally change the economics of manufacturing, computing, transportation, and quite literally, everything that depends on electricity, which in the modern world is almost everything. So what actually comes next on the road to 2027, and then 2030? Because the roadmap China has laid out is a lot more specific than most people realize. The immediate next step is integrating this magnet, along with the central solenoid coil, into the actual burning plasma experimental superconducting. Tokamak currently under construction. The reactor these components were specifically engineered for. That 2027 completion target is the milestone to watch first, because it's the point where these individually tested components have to work together in a fully assembled reactor under real operating conditions, rather than isolated bench tests. From there, the 2030 target for first fusion-based electricity generation becomes the number that actually matters to the outside world. Reaching that milestone, even in an early, small-scale, non-commercial form, would represent a genuine global first for a program moving at this pace, and it would put enormous pressure on other major fusion efforts, including ITER and various private fusion companies in the US and Europe, several of which have also stated ambitious timelines for the early 2030s. Longer term, the China Fusion Engineering Demonstration Reactor represents the actual commercialization step, a facility designed not just to prove fusion works, but to prove it can generate electricity reliably, safely, and economically enough to eventually feed a real power grid at meaningful scale. That's the step where "does this work at all" turns into "can this actually replace a power plant?" And it's realistically still a decade or more away, even under an optimistic reading of China's own roadmap. It's also worth watching how the rest of the world responds. ITER, the international collaboration this new magnet directly outperforms in stored energy, involves dozens of countries pooling resources specifically because no single nation wanted to shoulder fusion's enormous cost and risk alone. China building comparable, and in this specific case, larger, capability entirely through its own domestic program, without that same international cost-sharing structure, is likely to accelerate funding and political urgency behind fusion efforts in the US, Europe, and among private fusion startups that have been racing toward their own net energy gain milestones over the past few years. So let's put this all together, because both the fusion is basically solved excitement and the "this is just a magnet, nothing important happened" dismissal are missing the real picture here. The overly excited take, "China just solved fusion energy," isn't accurate, and it's important to be honest about that. No electricity was generated. Net energy gain, the central scientific hurdle that's defeated fusion researchers for 7 decades, still hasn't been demonstrated using this hardware. And key performance claims haven't yet received independent international verification, the way results from collaborative projects like ITER typically do. But the dismissive take, "it's just a big magnet, this doesn't really matter," badly underestimates what actually happened. Building a superconducting magnet at this scale, entirely with domestic materials, that successfully passes every acceptance test, is one of the hardest manufacturing and engineering challenges in the entire fusion field. Arguably harder than many of the physics problems fusion researchers spend their careers on. Getting the hardware right, at scale, reliably, is exactly the kind of unglamorous, expensive, easy-to-underestimate work that separates countries seriously building toward commercial fusion from countries that are merely funding research papers about it. That's the real headline hiding underneath the exciting one. China didn't just build a big magnet. It proved at record scale that it can manufacture one of the single hardest components in the entire fusion supply chain domestically, on schedule, as part of a roadmap with a real 2027 deadline and a real 2030 target for actual electricity. Whether that timeline survives contact with the remaining unsolved physics is still genuinely uncertain. But the hardware, at least, is no longer the excuse. Let's bring this together. China's Institute of Plasma Physics has completed and successfully tested the largest superconducting fusion magnet ever built. 582 tons, 21 meters long, storing 3 times the energy of ITER's equivalent magnets, built entirely with domestic materials after 6 years of engineering work. This is a critical component for China's burning plasma experimental superconducting tokamak, targeted for completion by 2027, with China's own roadmap pointing toward first fusion-based electricity generation as early as 2030. This doesn't mean fusion energy is solved. Net energy gain still hasn't been demonstrated with this hardware, and independent verification of these specific results isn't yet publicly available. But it does mean one of the hardest engineering problems standing between humanity and functionally unlimited clean energy just got solved at a scale nobody else on Earth has matched yet. Let's run through the numbers one more time. 582 tons, the weight of the magnet. 3 times the stored energy of the equivalent ITER components. 6 years of engineering work. 47 patents. Entirely domestic materials. 2027. The target date for the full reactor. 2030. The target for China's first fusion-based electricity. Individually, these are just numbers about magnets and timelines. Together, they describe a country making one of the most serious, well-funded bets on the future of energy that currently exists anywhere on the planet. We're going to keep tracking this story as China moves toward that 2027 reactor completion, and as the rest of the world's fusion programs respond to the pressure this creates. If this video helped you actually understand why engineers are genuinely amazed by this, not the exaggerated version, not the dismissive version, but the real engineering and the real stakes, hit subscribe, because fusion energy might be the single biggest story of this entire decade, and it's only just getting started. Thanks for watching. We'll see you in the next one.